Hello everyone. Today we are going to look at Electric Energy Systems Theory, Chapter 6, the Power Transmission Line by Elgerd. And we're going to solve some exercise. First exercise that we are going to solve is exercise number 6.4. It says consider the three-phase symmetric 230 kilovolt three-phase line with parameters R equals to 0.074 ohms per kilometer, L equals 12.12 times 10 to the power minus 4 Henry per kilometer, and C equals to 9.577 times 10 to the power minus 9 farad per kilometer. So A says that the line is 150 kilometers long and can be assumed to be a short line. Find the equivalent circuit elements. So we are going to solve the following exercise using Matlab. So first thing that we are going to do is note down the information that we have. So we're going to say exercise 6.4. So what do we know? We know Vs is equals to 230 exponent 3. R is given as 0.074. L is given as 12.12 exponent minus 4 equals. Then we have C is equals to 9.577 exponent minus 9. The length of the line is given L is equals to 250 kilometers, and the frequency is 60 hertz. Now the first thing that we are going to do is to find the equivalent circuit elements. So I'm going to say equivalent circuit elements. How can we find it? For R, it is simple. So R equivalent will be equals to R times the length L, which is, let's see, this comes to 11.1 ohms. So we can write it down here, 11.1 ohms. Now let's look at the inductor. Remember that the equivalent reactance is J omega C. So we're going to say J times 2 times pi times F, that's omega, times the inductance L multiplied by the length L. So let's see what this is. It is plus 68.537. Remember it's J. So J positive 68.5, we can say. We'll say. Now the equivalent reactance for the capacitor. To find the equivalent reactance for the capacitor, we have to follow two steps. So first we'll define C1. So we'll say, remember, reactance of the capacitor is equals to 1 divided by J omega C. So we're going to say 1 divided by J. Okay, don't mention J here. Say J omega is 2 pi F C. Okay, C is already defined here. So you get C1. Okay, now C equivalent as defined in the book is equals to, we'll just have a minus J. Remember that the capacitor is a minus J times C1 that we have found out just before times 2 divided by the length. This will give us the equivalent value for C. So the equivalent value is minus, okay, we can say 3693. So we're going to say minus J 3693. Okay, so that solves for A. We have found the equivalent second elements. Now let's see B. B says the line is open circuited and energized to a voltage level of 230 kilovolts at 60 hertz as measured at the sending end. Find the voltage at the open end. So we are going to find the voltage at the receiving end. So we're going to say voltage at the receiving end, and we are going to get this by voltage division, using the voltage division rule. Sure. Okay, so VR, we are going to say voltage receiving voltage is equals to, you want to see the absolute value, okay, this, which means the magnitude of Vs supply voltage multiply by, okay, we are going to say Ce, equivalent value for C, divide by Re, okay, the total impedance Le plus Ce. Okay, remember why I've said this? Because we want to find what is the voltage here, so we are going to use voltage division. So we are going to say Ce, okay, this impedance here, divide by the total impedance. So let's see what we get. This is correct. Okay, let's see another. So it is 234 kilovolts. Okay, now if you want to change this in per unit, it would be VR per unit is equals to absolute of PR, which we have found out, divide by Vs, which we are using as our base. So VR per unit is equals to 1.0189. So we can say that VR is equals to 234, 234.3 kilovolts. Okay, that solves question exercise 6.4. Now let's move on to exercise 6.5. So exercise 6.5 says the 100-kilometer open circuited line in 6.4 is being energized from a 500 MVA 20 kilovolt generator via a 500 MVA 20 to 230 kilovolt step up transformer. The generator has a 90% synchronous reactance and the transformer has a 14% leakage reactance, all based on the nameplate ratings. It is assumed that the generator excitation is adjusted until the voltage measures 230 kilovolts on the transformer HV side. The light is suddenly de-energized by opening the circuit breakers located on the transformer HV side. Compute the new voltage on the transformer HV side, assuming that the generator excitation is unchanged. So the first thing that we are going to do here is, again, find the equivalent circuit. So our equivalent circuit would look something like this. Let's start. Again, let's put down all the information that is given. The parent power is given of the generator, which is 500 megawatt. So it's times 10 to the power 6. Voltage is given as 20 kilovolts. Xg of the generator, X of the generator is given. So that is J, remember, times 90%, so it is 0.9. And xt, the transformer is J times 0.14. Okay, you can directly write this down here. So for the generator is 0.9. Okay, for the transformer is 0.14. This is the breaker that has been mentioned. Now we have to find again what is the equivalent values. So in per unit, so we're going to say line per unit reactance. So line, so we're going to say L equivalent per unit is equals to LE. Remember, we are still referring, the question says to refer back to 6.4. LE divided by VS squared multiplied by SG. Let's see what this is. So we're going to evaluate all this. So LE per unit is 0.64. So we're going to get 0.64. You can say yes, 64. And now for the capacitors, so C equivalent per unit is equals to CE divided by Vs squared multiplied by Sg. Remember, we are converting into per unit. So this is minus 34.9. Remember, it's minus J. Okay, so we have found the equivalent circuit. Now, in order to do computation, we need to reduce the circuit, reduce it to this. So how are we going to reduce it? We have to first add this impedance in series, and then whatever we find here will be added in parallel to this. Okay, remember this is 34.9. Okay, each of these capacitor is 34.9. Let's continue. So let's do the first part. So as I said, Z1 will be equals to the L per unit plus C per unit. So it's E per unit because we have defined CE. So what do you get? We get 34.25 minus J. Now continue, let's put it in parallel. So we have found this plus this is equals to minus J 34.25. Now we have to put this in parallel to this. So we're going to say ZE. Yes, we're going to say ZE is equals to Z1 multiply by, okay, this is a shortcut method to add in parallel, divide by total Z1 plus CE per unit. Okay, let's see what we get. we are getting minus 17.3. So this becomes minus j 17.3, and this here becomes xg, okay, xg plus xt. So we're going to say x is equals to xg plus xt. So let's see what this is. This is 1.04. So j 1.04. Yes, correct. Now we have found the equivalent reduced second. We can do the computation for the voltage on the transformer HV side. So we are going to say with the breaker closed, okay, with the breaker closed, the relationship of, okay, I'll just put it down here, V2 divided by E in per unit is equals to ZE ZE divided by X plus ZE. Okay, given, okay, it mentions, the question mentions that we are going to say VB is equals to 230 exponent 3. Therefore V2, okay, the question says here, let's just go back and say, it says compute the new voltage of transformer HV side assuming that the generator excitation is unchanged. And it also mentions here, it is assumed that the generator excitation is adjusted until the voltage measures 230 kilovolts on the transformer HV side. Okay, so we're going to say V2 is equals to 1 per unit. Remember why? Because it is 230 kilovolts. So 230 kilovolts divided by V base, which is 230 kilovolts, is equals to 1. Now we can say that the voltage E per unit is equals to V2 divided by whatever we have found here. Okay, this was the relationship. We said V2 divided by E. Remember, V2 divided by E per unit, when you are writing it down, is equals to ZE divided by X plus ZE. Now our E per unit will be V2 divided by PU, which we have defined here. So this will be in per unit. Let's see what it E is in per unit. We get 0.9398. So let's multiply it by the base. When we multiply it by the base, we will get VB times E per unit. We get about 216 kilovolts. So that's what the answer says here. Okay. I hope this is clear. Remember, when you are doing the question, you have to write all this down. This is just to simplify your calculation, because doing it by Matlab shows step-by-step calculation. So when you are redoing the question, remember to write all this down. So we have got the solution for 6.5 now. Now let's move on to 6.6. 6.6 says, we assume now that the line in exercise 6.5 is being energized and the sending end voltage of the line is kept at 230 kilovolts by automatic voltage regulation of the generator. So it is always kept at 230 kilovolts. Three 220 ohms Y connected load resistor are suddenly switched to the receiving end. A. By how many percentage will the voltage VL drop from its open circuit value computed in exercise 6.4? So let's start off with A. So the first thing that we have to do here again is to define our circuit. Okay. So the first circuit that we are going to draw will look something like this. Okay. We already had this. Okay. This is generator, transformer, the line model, and this is the load. So let's start computing. So we're going to say exercise 6.6. So again, Vs is given. Vs is equals to 230 exponent 3. Load resistor Lr is equals to 220. Okay, now we have to change all this to per unit to find the equivalent circuit here. So change to per unit, change to per unit. Remember, keeping in mind SB is equals to 500 exponent 6 and VB is equals to 230 exponent 3. Now R per unit will be equals to, okay, LR multiply by SB divided by VB squared. Okay, let's see. Okay, we have to define this here. So R per unit is equals to 2.08, we can say. So we can write it down here. 2.08. Okay. Now let's move on to the other components. Yeah, other components we already have defined. So we can just write it down. Don't have to compute it again. So this was J 1.04. Okay. So let's compute the others. Z in 1 is equals to X times CE per unit divided by X plus E per unit. Okay, when we are solving for the equivalent circuit. 1.07, and then Z in 2 is equals to Z in 1 plus LE per unit. Okay, you get 1.71. Okay, now this has been given here, so let's write it down again for it. So it's clear for you what we are doing. So this is J 0.647, small j, this was a small j, this is J 34.9, and this is 2.08. So what we are doing is reducing the second. We have to go from here, okay, to here. So what we have done next is we have removed the generator, so we are left with only the uh, impedances. So after addition, okay, so we are going to add this in parallel to this. So that's what I have shown here, Z in 1. So we're going from left to right. So we're going to add 1.04, which is X, plus in parallel CEPU. So this is how we add in parallel. So we get Z in 1. Now Z in 1 will be added in series to LEPU, the equivalent inductance in. So once we get that, we will again add Z it in parallel to this capacitor. So we're going to say Z in 3 is equals to Z in 2, okay, multiply by CE per unit, divide by Z in 2 plus CE per unit. So finally we will arrive to Z in, which will be equals to R per unit, so R per unit plus Z in 3. So let's see what we get. Okay, we get 2.07. Okay, and till here we have 1.0, 1.08. So we can write it down here. So first we can say this is 1 point, okay, J 1.808, and this here is 1.71, J 1.7, sorry, J 1.71. Okay, now we have found that Z in is equals to R per unit. So we can find what our load current is. So the load current in per unit is equals to IL per unit, VR per unit, divided by the magnitude of Z in. So we get 0.3697 per unit. So we can start computing A now. So I ask us what is the voltage drop. So percentage drop. you can say drop is equals to V R per unit minus VL per unit, okay, divide by PR per unit times 100. Okay, we have to define this first. VL VL per unit is equals to IL per unit times R per unit. Okay, this was the current at the load. Okay, remember current at the load. So the current flowing here, we can find the voltage by multiplying the impedance. So we get 0.76 per unit, and the drop is 24.55. So we can say here that the percentage drop is 24.5% for A. Now B, how many megawatts will the resistor consume? So let's compute. So B is asking how much power will the load consume. So the power per unit will be equals to VL per unit divided by CE per unit. Okay. Sorry, V per unit or 2 divided by R per unit, and that's in per unit. So just want to know the power, you'll say P per unit times the S base. So it is about 142 megawatts. Yes, 142 megawatts. 142 megawatts. Okay, if you shift this 1 2, this becomes 6, becomes megawatts. Now C says to compute the megawatt and megawatts flows at the sending end. So we're going to look at V0. So what we have to do, we know what is IL and VL. We have to find what is I2, and then once we find I2, we will know what is I1, because I1 is equals to I2 plus IL, and the voltage in parallel will be same. So we'll understand what is the voltage drop. So part C, megawatt and megawatt at the sending end. So as mentioned, first we'll compute what is I2. So I2 is equals to VL per unit divided by CE per unit, and then I1 will be equals to, this is 0.22, and I1 is equals to IL per unit plus I2. Get our I1. Now V at the sending end, VO per unit is equals to VL per unit plus L per unit multiplied by the current that we have just found out, I1. So we get our voltage in per unit form. Now we want to know what is the reactive power. Remember that the active power we've already computed, which will be equal to 142. Reactive power would be the power on the inductor and the two capacitors. So we're going to say Q per unit be equals to LE per unit multiplied by the absolute of I1 squared minus the absolute of V0 per unit squared divided by CE per unit minus absolute of, okay, remember we are taking absolute because we just need the magnitude to compute the reactive power, VL per unit to divide by CE per unit. See if we can run this. Yes, 0.054. Now very simply S will be equals to S base times P per unit plus Q per unit. We should get the value. Okay, okay, we get, so after computing we get 142 megawatts plus 26.98 megawatt. Okay, you can see this here. 1, 2, this becomes 6. 1, this becomes 6. So this is 26.98 megawatt. So I hope you have understood what we have done. Remember, when you are redoing the questions, either you are doing it again on Matlab or on paper, remember to write each steps, because here we have done calculation for each step. If you have questions, please do email me. Thank you very much.